Hi guys, this is going to be a quick walkthrough of a few specific lessons from Unit 4 Processor Fundamentals of the Cambridge 9618 AS Level Computer Science syllabus. This video should be watched with reference to the 4.2 or Unit 4 Part 2 note that we've been doing in class. So please make sure that you guys have that note with you before you start watching this recording. But feel free to watch this recording even if you don't, just for a quick refresher. But yeah, without further ado, let's begin. This is Processor Fundamentals, Unit 4, Part 2. Right, so the first thing we'll talk about is interrupt handling, which is something that we couldn't talk about before, but we will be talking about in this video. And for those of you that are referring the note, this is something that you see on page 2 of the note, interrupt handling. Okay, first up, what's an interrupt, guys? An interrupt is a signal that's sent from a device or software to the processor. And think of an interrupt like your brother or sister walking into your room while you're doing something. And your brother or sister is demanding your attention. Now, of course, whether you give that attention is up to you, but hopefully you do. The CPU has no choice. When an interrupt comes along, it has to service or look at that interrupt and pay attention to it. That's essentially what an interrupt is to the CPU as well. The CPU receives a signal from a device or software, specifically asking it for some sort of attention, asking it to focus on the interrupt rather than what it's doing now. And this will therefore cause the processor to temporarily stop, right? The keyword here is temporarily stop what it's doing and service the interrupt, right? So what it means by temporarily stop, guys, is that it's not going to permanently stop whatever it's doing. It's going to temporarily stop, meaning that it's going to stop whatever it's doing now, look at the interrupt, and then after that's done and dusted, it's going to get back onto its normal task. And servicing the interrupt essentially means to go and solve the interrupt. What is causing the interrupt, whatever the cause of the interrupt is, that needs to be resolved. So servicing the interrupt essentially means to resolve the interrupt. Now, interrupts can occur in one of 4 major ways. It can happen as a result of a timing signal, can happen as a result of a hardware or software error. It can happen as a result of an I/O process, an input-output process, or it can happen as a result of a user interaction. These are all 4 different ways that is so-called disturbances to the CPU or interrupts to the CPU can occur. Now let's discuss a quick example of an interrupt, what a practical example of an interrupt could be. Let's imagine, guys, that you have a printer. Let's imagine that we have a printer. And let's say that this printer is connected to your CPU like this. And let's say that the CPU is currently running a program from the RAM. And this program could be a program like Microsoft Word, where Microsoft Word is currently running instructions on the CPU to do what? To maybe ask the printer to print out some notes or, print out some hard copies of whatever document you've been typing on Word. So it's running instructions to send signals to print hard copies of a document, right? It's sending signals to the CPU and thereby in extension to the printer to ask the printer to print out hard copies of a document. And, print spooling and other buffering techniques might be used here as well, but we don't want to get into the details of that. But you can imagine that the CPU is now actively running instructions, asking the CPU to, print out sheets of paper, whatever the document or the sheets of paper is about. Now, let's say for some reason there's a problem. Printer runs out of paper. What happens now? The CPU is busy telling the printer to print these documents, but it can't print these documents because the printer has run out of paper. So what does it do? The printer sends a signal back to the CPU, and this signal is, lo and behold, the interrupt. So what does the CPU do? The CPU will have to stop whatever it's currently executing and look at this distress signal that is sent by the printer, asking the CPU to know, hey, I've run out of paper. Can you try and ask the user to maybe remedy the situation? So what does the CPU do? The CPU has to momentarily, like I said, stop whatever it's doing. Whatever it's doing is sending signals to the printer to print documents, but there's no point in continuing to do that because frankly, there are no papers to keep printing the document. So the CPU has to momentarily stop what it's doing, service this interrupt, which means to maybe run a program that displays an error message on the screen that informs the user that the printer has run out of paper. That's an example of an interrupt service routine, which is a program that runs to resolve an interrupt. And hopefully, if the user sees that interrupt, by interrupt, I mean sees that error message, hopefully the printer will be replenished the papers and it can continue doing its job. So the idea is that the CPU is doing something goes wrong, whatever went wrong sends a signal to the CPU. The CPU has to stop what it's doing, service the interrupt, and hopefully if everything works out, it can carry on with whatever it was previously doing once the interrupt, beg your pardon, has been serviced. Okay, that's a quick example of an interrupt. Hopefully that makes sense to you guys. And now let's discuss about the exact steps that go into an interrupt. You need to know this for your AS level exam, and you will get questions asking you to describe this process in words or maybe even to draw a flowchart. We start off at the top. Interrupts are checked at the end of the fetch, decode, execute cycle, not before, at the end. So once the current execution has finished, right? Once the current instruction has finished executing, that is at the end of the fetch execute cycle, the CPU will check for interrupts. But how exactly does it check for interrupts? The CPU checks if the interrupt flag is set. What exactly does this mean? Now, while the CPU was busy doing something, while the CPU was busy executing instructions, during that time, the printer, for example, may have run out of paper. So frankly, the CPU might not be aware when exactly the interrupt occurred, because the interrupt may occur well in advance or during the fetch decode execute cycle. Now, as a result of that, we need to have a way to maintain or keep track of an interrupt that may have occurred during a previous instructions fetch execute cycle, because frankly, the CPU only is able to attend to these interrupts after the current fetch decode execute cycle is done, isn't it? So the interrupt flag is essentially a number that you can imagine is stored in something called the interrupt register of the CPU, which you can imagine contains a 1 or a 0, depending on whether an interrupt has occurred or not. Of course, there's a bit more nuance that goes into this, but as far as your AS level understanding needs to be considered, this is more than enough. So the interrupt flag in the interrupt register of your CPU is set. And whenever the interrupt has occurred, as soon as the interrupt is occurred, a control signal will be sent to the sort of interrupt register and thereby the CPU to keep track of this interrupt, so that whenever the CPU is ready, it can take a look at it. So at the end of the fetch decode execute cycle, if the interrupt flag is set, which hopefully did happen if an interrupt occurred, what the CPU does is it first identifies the source of the interrupt, where has the interrupt occurred. Then it saves the current register contents. Whatever it was currently executing, it saves its contents into the RAM. And then after that, it loads and runs the ISR, which is abbreviation for interrupt service routine, right? Loads and runs and ISR based on the priority of the ISR, whether it's a high priority or a low priority interrupt. And once that's done, once the interrupt has been serviced, it will restore the process that it was previously executing and re-enable low priority interrupts. That way they can, continue executing. Even the low priority ones that have been overtaken by the high priority ones can continue executing. And once this is done, the process returns back to normal execution. Okay, so first of all, in summary, at the end of the fetch decode execute cycle, the computer or the CPU checks if the interrupt flag has been set. If yes, what are the 4 steps that happen? The source of the interrupt has to be identified. This is maybe the printer, for example. Then the current register contents are saved in the RAM. After that's done, we know that the current execution can be resumed now, so we'll not worry about that. Next up, we'll load and run the interrupt service routine, which is the program that's responsible for resolving the interrupt. For example, it could be the program that's responsible for showing you an error on screen when the printer runs out of paper. And finally, once that's serviced and once the interrupt has been successfully resolved, the previous process, in step number 2, we save current content registers. Beg your pardon, we save the current register contents. Those register contents are restored, thereby allowing us to continue what we were processing earlier and also re-enable any low priority interrupts and carry on with the normal execution process. This is all you need to know for interrupt handling. And feel free to refer to, I believe, page number 2. It was page number 2, yes. Feel free to refer to page number 2 and maybe even draw this flowchart in the space given on the note to complete your understanding of interrupt handling. But this is it. Hopefully, you guys understood that. Next up, we're going to look at a very interesting section in the syllabus called the 2-pass assembler, which is mentioned in page number 3 of your note. All right, so let's get started with that. Now, the 2-pass assembler is a program that's responsible for converting assembly language code into machine code, which is the only language that the CPU understands. Now, assemblers fall into the category of translation software, which is a kind of system software that is responsible for, converting high-level language code into machine code. Frankly, the CPU doesn't understand anything but machine code, which is just plain old binary. So it is important that we write programs in a high-level language, but then convert them into machine code in order to run them on the CPU. Now, an assembly language program is what you see on this screen right now. It's composed of 6 different instructions, which is also a formal way of writing programs, although it is not something that is used in the industry, for example, because it's far too complex to write complex applications in assembly, because assembly is too low level. But you can still use assembly to debug programs or debug applications, and also decompile and deassemble existing applications to see how they behave. And most importantly, as students, why we learn about assembly is so that we understand what goes into the operations that we take for granted in the computer. Now, for instance, if you were to say something as simple as x equals 5 plus y, setting the variable x to 5 plus the variable y. The problem with that is that it seems quite simple, but frankly, it requires a lot of operations under the hood. It requires loading y from RAM, adding that result, adding the value of y to 5, and then storing that result in wherever z is stored. So it's a very lengthy process that often we take for granted, but assembly helps us understand how individual operations like x equals y plus 5 or 5 plus y is actually composed of, it helps us understand that individual operations, simple operations such as that, is composed of much more simpler, but many of those simple operations under the hood. But again, assembly language is a mnemonic-based language. It's based on these so-called opcodes that represent binary under the hood, right? So in reality, assembly code can be very effortlessly converted to machine code by replacing these mnemonics with respective binary codes based on something called the instruction set. But we'll look at that. But I wanted you guys to have an idea of what an assembly program looks like. It looks like this: line numbers 1 through 6. where you have assembly code instructions. Sometimes you have blank lines as well, because sometimes these programs are written by humans, so they might leave lines. And you can also have comments. Comments are also applicable. Of course, what not found and found are, they might look a little suspicious. We'll look at that. So don't worry about not found and not found for now. Now, like I said, an assembly program is a mnemonic-based representation of machine code that helps us understand how our program behaves. However, the CPU only understands machine code, which means that this assembly code needs to be converted into binary, in other words, machine code, by a kind of assembler called the two-pass assembler, which is a translation software, guys. A two-pass assembly is a translation software that's responsible for converting assembly programs into machine code. Now, how does the two-pass assembler work? Frankly, we can't go there yet. We need to first understand what are the common parts we see in our assembly program. We first have these things called labels, which are not found and found. Labels in assembly code, we don't really meet in AS as much as we do meet them in A2, just because it's quite complex to work with them in AS. And don't worry, if this isn't complex for you, we'll be meeting them in A2. But the idea here is that labels are human readable aliases for sort of memory locations, or you can imagine for line numbers. So for line number 1 and line number 6, you can imagine that they've been given aliases of not found and found. So the idea is that when you say JPN found and JPE not found, which are both assembly language programs or assembly language instructions, what are we actually referring to by found and not found? We're referring to line number 6 and line numbers 1. So the idea is that found and not found are references to previous or after lines of code, which helps us as human programmers effortlessly refer to lines of code that we have previously or planned to write without having to worry about explicit memory locations. So labels are aliases, or essentially names given to line numbers or memory locations. Now, having understood that, of course, I can quickly erase this stuff. The next thing that we have is opcode and operands. LDD20 is an example of an opcode and operand. The same thing applies to all the other instructions, although the OUT instruction is a special instruction which does not have an operand. So keep in mind, this is an opcode only instruction. There is no operand. And then there are comments as well, just like normal programming language code. Assembly code might also have comments. Now, the two-pass assembler, like I said, is a translation software who's responsible for converting assembly programs into binary. But it's called the two-pass assembler because it traverses the code 2 times, meaning it goes through all the lines of your program 2 times in order to convert it to machine code. Now, what's these two passes? What are the two passes? What exactly happens in these two passes? Let's take a look at that. Pass 1 in the two-pass assembler. Again, remember guys, don't confuse yourself. We are in the process of understanding how do we convert assembly code into machine code. And this is done by the two-pass assembler. And we have already looked at the structure of assembly code as well. Our time now is to take a look at what exactly happens in those two passes. Starting off with pass number 1, the analysis pass. Now, in the analysis pass, this so-called assembler program, this translation software, traverses each line or traverses through each line of our assembly code and does these 5 things. Number 1, ignores comments and white space. It removes comments and it removes white space because frankly, that is not important for the logic or the operation of the program. Number 2, checks the opcode of each instruction against the instruction set. Checks whether the opcodes are legitimate. Are we writing illegitimate opcodes that the CPU doesn't understand? If so, the program cannot be assembled. But if it is all legitimate, then the opcodes must match those in the instruction set. So we should be able to carry on and proceed normally. Now, if all the opcodes match as we go through, the next thing that we do is we add labels and their addresses to a symbol table. Now, I hope you guys remember what labels are. Labels are stuff like not found and found. And once we load these instructions, LDD20, CMP, #0, JPN found, so on and so forth into memory, those memory locations will be the ones that are being aliased by not found and found, the labels not found and found. What we can do with that is we could actually create another table that maintains references to where not found and found are actually referring to. So not found is referring to the memory location where LDD20 is stored. Found is referring to the memory location where OUT is stored. So once they actually get stored in RAM, we can refer to those locations and store those addresses in a separate table called the symbol table. Again, if this doesn't make sense, guys, don't worry. I'll be walking you through a very practical example soon. So maybe, give it a minute, wait for me to complete my full explanation of this, and then you can probably rewind and maybe ask me any questions after the recording itself. Step 4 is expanding macros. Now, macros are not something that we study in depth in our syllabus, but a macro can be thought of as an assembly level subprogram. So the idea is that, guys, just like how when we write pseudocode or maybe Python, we write functions and procedures. Assembly code could also have these so-called macros, which are subprograms or functions and procedures. Now, when we write those functions and procedures in assembly, it's important that we expand them, or we take the so-called function and procedure calls and replace them with the actual full function and procedure. So in other words, if you take an assembly language program that has 4 lines of code, let's imagine that the second line of assembly code is actually a function call. What happens in this expanding macro stage is that this assembly code function call, which is referred to as a macro, is replaced by the actual function, which might be a much larger function. Of course, this is a very simple way of understanding this as a replacement, but there's more that goes into this process. But like I said, the idea is that simple function calls or procedure calls or subprograms at assembly level are expanded by their full form, which is what expanding macros means. But that's all you need to know about macros. Nothing more, nothing less. Number 5, each instruction that we go through in the pass is allocated memory as well. All right, good. So I hope this is all clear with you. I hope there's no doubts. So we shall now actually see pass 1 in action. Okay, so hopefully you can take a minute to digest what you see on screen. Here you guys can see the so-called assembly language program. Where each of these lines represents a single assembly instruction. And then you can also imagine that what you see on screen is, actually, you don't have to imagine, you actually do see them on screen. I don't know why I refer to this as imagine, but you can see on screen, in addition to the assembly language program, 3 more tables. You can see a RAM table, which shows you addresses and data locations, which are currently empty. An instruction set, which shows you all the opcodes that this CPU architecture supports, along with their respective binary codes. Sorry, I'm in the wrong slide. You can see their opcodes and the respective binary codes they support. Right? Hopefully that makes sense. You can see the instruction set here, and you can also see an empty symbol table. But what this symbol table does, we'll understand, don't worry. So let's hold on to the idea of a symbol table soon, so that we can, let's hold on to that idea so that we can take a look at it when we get to that point in the discussion. Okay, so this is what you see on screen. You see an assembly language program on the left, you see the RAM, you see the instruction set, and then you see the symbol table. Okay, now it's time to start executing, or rather, sorry, small mistake. We won't be executing, we'll be assembling. We'll be going through the first pass of the 2-pass assembly. Now, what you see highlighted here in red color is the current line that we are interested in assembling. This first line says not found LDD20. Now, in pass 1 of, which is the analysis stage of the 2-pass assembler, what we do is we allocate LDD20 a memory location. Maybe LDD20 is allocated address 0 of the RAM. And then, slightly before we allocate memory for this, we do one more thing, which is to check if LDD is a valid instruction in the instruction set, which it is. LDD is a valid instruction. So therefore, I put a tick here to signify that this is a valid instruction. And then, once this is done, the comments have been removed as well, along with the fact that the label not found, which is a reference to line number 1, has now been added to the symbol table, but its address has been set to 0. Why? Because not found is really a reference to this instruction LDD20. And where is instruction LDD20 stored? In address 0, which means that not found is another name for address 0. Hopefully that makes sense to you now. That's what the symbol table contains. Next one, we go to the next instruction, CMP hashtag 0. There we allocate memory for CMP hashtag 0 in the address soon after address 0. We allocate memory for CMP hashtag 0 in address 1. Therefore, we check if CMP is in the instruction set. And finally, last but not least, what do? We will continue. Frankly, I was under the assumption that we'd have one more symbol to worry about, one more label to worry about, but we don't. So the only thing that we do with this stage is that we just add the instruction to RAM, we allocate it memory, and we check to see if our so-called instruction is a valid instruction. Is CMP in our instruction set? It is, so we carry on. Next, JPN found, that too gets memory location 2. It is a valid instruction, and we move on. Then JPE not found gets a memory location 3, that therefore gets allocated to memory location 3. And finally, we check to see if JP is in our instruction set, which it is. So therefore, that is also valid. Now, the next line, line number 5, is a white space. It's just a blank line. So we ignore that. That's something that we do with the first pass. We ignore comments and white space. Then number 6, line number 6, we encounter the OUT command, which means that we allocate space for the OUT instruction in address number 4. We check if OUT is valid, which it is, which gives us the green check mark of success. And finally, we have encountered yet another symbol, which is this label found, which is therefore added to the symbol table. But now, since found is essentially a reference to the line number or the command OUT, wherever OUT is stored, which in this case is address 4, is the address of the found symbol or the found label in the symbol table. So now we have our labels, we have their addresses in the symbol table, along with all the instructions assembled to RAM, and also all the instructions checked and confirmed to be valid instructions based on the instruction set. That's pass 1 complete. So at the end of pass 1, guys, we end up with a beautiful set of instructions assembled into RAM with each given respective addresses. And we also have created a symbol table where all labels that are aliases to particular commands have, also been allocated addresses based on where their respective corresponding instructions are stored in the RAM. Nice. Okay, that's the end of the analysis pass. Then we move on to the synthesis pass. This is very easy. In this pass, as the assembler traverses through each line of code, it does 3 new things. It translates opcode into binary, it resolves labels using the symbol table, and constructs the full instruction binary code. So it translates opcode into binary based on the instruction set, removes labels, resolves labels using the symbol table. So you know how those labels not found and found have been given addresses 0 and 4? Those addresses now replace the actual not found and found in the RAM. That's what resolving means. And finally, we construct the full instruction binary table. Oh, my bad. We construct the full instruction binary, which means we replace all the mnemonic-based commands with actual binary commands. This is the synthesis stage. So let's take a look at what happens in the synthesis stage. So keep in mind, now we have achieved synthesis. We are beginning synthesis as a result of already achieving pass number 1, which is analysis. Keep in mind, we have to have completed analysis before synthesis can occur. Now in synthesis, what happens, guys? Our symbol table and RAM are now full of instructions and labels. So in the second pass now, we go through our instructions once again. We go through all the instructions once again, but this time, what do? We replace LDD with the respective opcode code from the instruction set. So the opcode LDD has the code 000. That is now what replaces LDD in the RAM. And then the 20, the operand, has been represented in binary as well. Cool. So we are now in the process of converting all of our assembly code instructions into nice and very concise assembly code instructions. Machine code instructions. We're now converting each of our assembly instructions into machine code. Pretty straightforward, right? Then what do? We do the same for CMP. CMP's opcode code in binary is 001, and its respective operand is 0, which has been written in a 5-bit binary number 0000. Then JPN found. Now, this is an instruction that requires a reference to the symbol table. Not only does it have to resolve JPN from the instruction set as 010, it also has to resolve what found means. But that can be located from the symbol table that we created in pass number 1, where we can look up what found means. Found is a reference to address number 4, and we represent 4 in binary as the operand in front of the opcode JPN. But now it's all in binary. We do the same for JPE. JPE's binary code is 011, whereas its label not found is replaced by all zeros, which is the address of where not found is stored. Finally, OUT gets the opcode binary code 100, and frankly does not have an operand. So therefore, we can allocate it an operand of 00000, essentially making it nothing. It has no operand. And of course, the CU, the control unit, is smart enough to know that these instructions do not need opcodes. So, these instructions do not need operands. So even if the OUT instruction has a bunch of zeros in front, the CU is smart enough to ignore that and carry on with the normal OUT operation, the output operation. And finally, ladies and gentlemen, you end up with a fully binarized, a fully machine code level program that, like I said, is in binary. But there's a few more things that you do to complete this entire process. What we end up in the RAM right now, as per your syllabus, is referred to as object code. Now, what this means is that it is binary. It is binary, sorry, but to a certain extent, which means that sometimes some symbols, some labels may still not be resolved. Now, of course, the example we took is very simple, but you have to keep in mind in reality, assembly code instructions or assembly programs may actually refer to other assembly code instructions or other assembly programs. You can think of it as, you calling other submodules or library programs. You can do that in assembly as well. So for instance, those kinds of external references may still not be resolved as a result of the synthesis stage. So what we end up at the end of synthesis is a form of partially binarized code. It's not fully binary, but it's partially binary. Of course, in this example, it's fully binary, but in reality, because of external references, external labels, external libraries, it may not be fully binarized. But whatever said and done, what we end up with after this is that we need to convert our object code into an exe, an executable file, in order to run it through something called a linker, which is the final stretch, which allows us to resolve external libraries, labels, and also, if necessary, relocates addresses, which completely converts our object code, which may contain still some unresolved references, into fully binarized code, which is an executable file. This is all now in ones and zeros. This is now fully machine code. But then finally, to run this program, we have to use another software called a loader, which loads up the executable in memory, sets up the program counter to start executing, and then the host is set loose. The program starts executing. So once you have resolved the object code, you have to link it to any external references if required, external libraries, external labels, whatnot, and then create the executable file, which is fully binarized, it's fully machine code, which then has to execute when loaded by the loader, which can take that executable, load it into memory, set up the program counter, and let the program do its job. So in final statement, guys, the 2-pass assembly process starts off with assembly code, followed by pass 1 analysis, which creates the symbol table and the so-called fully broken down or assembled or analyzed assembly code mnemonics in RAM, which is then synthesized to make sure that they are converted to binary, making sure that any symbols and labels are resolved. And what you end up with is object code. But to go from object code to executable, you have to link the object code with any external references using the linker, followed by creating the executable file, which you can then execute by using a loader. But that is the 2-pass assembler summary. Okay, that is it. Take a minute to digest this all, guys. Rewind, take a break, take as many time as you want to make sure that you guys understand this. But if you have any questions, do let me know. We're now one before the end of this sort of lesson. We have one more lesson to cover, which is binary manipulation. But before that, we have to cover binary shifting. Binary shifting, also known as bit shifting, is a very simple process. It's a very simple topic, which is far simpler than two-pass assemblers. But the idea with binary shifting, guys, is that it's a process of taking the bits in a register and moving the bits a given number of places within a register. So for instance, if you have a register with the binary sequence 0, 1, 1, 0, 1, 1, 0, 0, you can do something called a right shift. One right shift, which means that all the numbers in this original register now move one place to the right. One place to the right. And as a result, any vacant locations may be replaced by zeros or ones depending on the type of bit shifting you use, the type of binary shifting you use. So when I say types of binary shifting, does that mean that we have multiple types? Yes, of course. The first type of binary shifting we have is logical shifting, where we shift the bits of an unsigned integer. Very important. It doesn't work for signed, it works for unsigned. We shift the bits of an unsigned integer left or right of a register, replacing vacant locations with zeros. So any of the locations that become empty as a result of shifting the bits left or right, we replace with zeros. So what exactly happens with logical shifting, guys? If you take this number here that you, oops, my bad. If you take this number here that is given to you in binary, 0, 1, 1, 0, 1, 1, 0, 0, this number represents 108 in denary form. Now, you can do a logical shift right, which is abbreviated as LSR, as an assembly code instruction. Keep in mind, LSR is an assembly code instruction which might come to the exam, but what does it mean? It stands for logical shift right. And when you say logical shift right #1, this means you shift the entire number one space to the left, right? My bad, one space to the right. So what that means is every single number goes one space to the right. And as a result, you end up creating a vacant location on the left-hand side. No, that location ends up getting a 0, which, as the definition itself suggests, all vacant locations are replaced with zeros. And this 0 ends up getting kicked out of the right-hand side of the register. But that's okay, because as long as you kick out zeros and not ones, you won't lose precision or accuracy of the number. But what's more important is that you realize the qualitative effect of this. When you shift a number logically to the right once, right? Let me repeat that. When you shift a number logically to the right once, you end up dividing that number once by 2. So 108 divided by 2 gives you 54, which, if you want to check, is what this binary sequence, the shifted binary sequence, represents. So you can actually confirm this by checking this, which is the sum of the binary digits ending up at 54. So we can confirm this by doing 2 plus 4 plus 16 plus 32. So if you add them up, you'll end up getting 54, which indicates that it is indeed dividing the number by 2. And if you do the same thing, but a logical shift left, you'll end up multiplying the number by 2. Which will end up giving you 216. And logical shift left can be written as LSL with #1, indicating a logical left shift of 1. But keep in mind, you can change this number 1 to 2, to 3, to 4, any number, depending on how many shifts you want. And on the top, you see a summarized form of generally what effect these logical shifts have. A logical shift left of n digits results in a multiplication of 2 to the power n, whereas a logical shift right of n digits result in a division of 2 to the power n. All right. So in other words, if I were to give you a quick example, what if you logically shift left, your register by 2 positions? What will happen then? If you logically shift left by 2 positions, you'll end up multiplying your number by 4, which is 2 times 2. In other words, 2 to the power 2. But if you, let's say, logically shift right by 3 positions, what happens then? You're dividing by number by 2, you're dividing your number by 2, and again by 2, and again by 2. That's what a shift of right means. A shift of right of 3 means, which means that you're dividing the number by 2 to the power 3, if not 8. Okay, that is 2 times 2 times 2. So keep in mind, a logical shift left or right of n digits is equivalent to a multiplication or division of that number by 2 to the power of that many n digits. All right, that's logical shifting. Feel free to try the questions given on the tute for you guys to understand this better. And again, you can check this out in page number 7 and 8 of the tute. Then we have arithmetic shifting. This is very important. Arithmetic shifting is done for signed integers, where you take the so-called bits of your register and you shift them left or right, preserving the sign bit of the number, making sure that the MSB, the most significant bit, is not altered. So if you take this number here, treat it now as a signed number, where 1 here represents the 2's complement form sign bit, which is -1. If you consider this -1 as a sign bit, which now represents 128 negative, and if you add them up, you'll end up representing -20 for this number now. Now, this number, if you want to shift, you can't just shift this 1 out and carry on with your life. You have to make sure that that 1 remains constant, right? That sign bit must not move. So when you shift left or right, wherever, the 1, the sign bit, be it a 1 or a 0, the sign bit must be consistent. It must always stay the same. But you can thereby move all the bits to the right of the sign bit, left or right, as you need. So keep in mind, you keep this place position constant, and you can thereby move the bits left or right. So for instance, if you take -20 and you shift left arithmetically by 1, you end up shifting all the numbers except this one, which gets kicked out, 1 to the left, right? And keep in mind, the sign bit 1 makes sure that it remains its same position, right? It doesn't change. And finally, you introduce a 0 on the right-hand side of the register to make space or fill in the space created by that vacant position. And this can be represented in assembly as ASL, but it's not officially introduced by the Cambridge syllabus, so you don't have to really worry about this. But ASL can be thought of as arithmetic shift left, which performs the same operation. It multiplies the number by 2, if you do a left shift of 1, and if you do a left shift of n, it multiplies the number by 2 to the power n. So -20 becomes -40. And what if you do the same thing the other way? Same thing, same idea. You shift all the bits except the sign bit 1 to the right, right? 1 to the right, making sure that the sign bit stays the same, right? But you do have to keep in mind that here, in this occasion, you're creating a vacant space on the left-hand side. Now, when you create a vacant space on the left-hand side, guys, that vacant space must be occupied by a copy of the sign bit, not a 0, not a 1. Whatever the sign bit is, a copy of that, right? That's for left substitution. So if you ever create space, vacant space as a result of shifting right, as a result you create vacant space on the left-hand side, please fill in those vacant locations with 1s. Very important. But as usual, doing that will ensure that you end up getting -10, which is halving -20. And the operation equivalent to halving the number is an arithmetic shift right of 1. And the same principles apply. An arithmetic shift right of n is equivalent to dividing the number by 2 to the power n. That's arithmetic shifting for you. And finally, method 3, we have cyclical shifting or cyclical shifting, however you like to pronounce it. It's about shifting the bits left or right of a register such that the bits shifted out from one end is introduced from the other end. So you sort of cycle values so that none of them are ever lost. So for instance, if you do a cyclical right shift, right? A cyclical right shift of 2, right? Again, this is not an official assembly code, but it's not an official assembly language instruction, but it's just an abbreviation of cyclically or cyclically shifting right by 2. Keep in mind, CRS Hashtag 2 is indication to cyclically right shifting by 2. But what does this mean? This means that you move all the bits of your register, consider this to be the original register, 2 spaces to the right. As a result, what happens? All these bits move 2 spaces to the right, and the bits that get dislodged, circle back to the end of the register. Okay, hopefully that makes sense to you. The same thing applies to cyclical left shifts, where if you were to do a cyclical left shift, guys, in that occasion, what will happen? You'll end up introducing the bits that you kick off from the left-hand side back to the right-hand side. But that's cyclical shifting or cyclical shifting for you guys. That's the idea. Finally, we meet the last topic, which is bit manipulation, which is introduced to you in the note on page number 9 and 10. Okay, what is bit manipulation? Bit manipulation allows each bit of a register to be individually checked, set, reset, or toggled. Now, what does this mean? Imagine you have a register full of ones and zeros. Imagine it's an 8-bit register. What if you're interested in checking if the 7th and 6th bit are working properly? What if you want to check if they're on? How would you do that? Like, do you go and count those bits? I mean, do you go and check those bits? But how exactly do you check them? That's the discussion of this topic. If you want to independently or individually check if bits of interest in a register are on or off, you can use bit manipulation techniques. There are 4 major operators that can be used to bit manipulate. You can use the AND operator to check. You can use the O operator to set bits. You can use the AND and NOT operators in conjunction to reset. And you can use the XOR operator to toggle. Those are the operators responsible for bit manipulation. We'll start off with the check operation. Let's say that we wanted to check if the 5th and 6th bits in this register were on. What are the 5th and 6th bits? That's this bit and this bit here. Now, at a glance, it looks like these bits are on. But let's say we want to programmatically ensure that these 2 bits are on. How exactly do we ensure that these 2 bits are on? What we do is we create a new binary number, where in this new binary number, every bit is 0. And keep in mind, this binary number must be as large as your register. So if it's 8 bits, the binary number that you create here must be 8 bits as well. Every bit in this binary number is 0, except the 2 bits that you intend to check. So you end up representing 2 ones in the position 6 and 5, which is where you want to check if the register is on. Right? This is called the bit mask. This is called the bit mask, guys. And the idea is, in this bit mask, you end up representing 2 ones for position 6 and position 5 of the register, which is essentially the place where you want to check if your register has a 1 or not. So given that the bit mask has now been created, essentially you assigned ones to the bit mask where you want to check the 5th and the 6th bits, you can now represent this bit mask as an assembly language instruction. Now keep in mind, we're doing a check operation. If you remember, what is the instruction responsible for the check operation, guys? What is the logical operator? It's AND, isn't it? So what you could do is you could represent an instruction saying AND, and you could represent the bit mask in binary as well. What is this number in binary? This is going to be 64 plus 32, which should give you 96, isn't it? Yes. So there you go. You end up with the bits mask of 0110, 0000, and the so-called assembly code instruction that represents the exact same thing, which is AND hashtag 96, which represents that you're ANDing, you're performing a bitwise AND operation on each of these bits on the bit mask of 96. Let's perform a bitwise AND operation. What does it mean to perform a bitwise AND operation, guys? You take each bit independently and you perform a bitwise operation of AND on each of them. So in this case, you take 0 and the 0 on the original register and the 0 in the bit mask, and you perform an AND operation on both of those. What's 0 and 0? That's 0. What's 1 and 1? 1. What's 1 and 1? 1. And you keep doing this. You keep doing this bit by bit, comparing to see if the two fall into the correct constraints of the AND operator. That's 0, that's 0, that's 0, that's 0, and this one, and the last one is also 0. So what you'll realize is, as a result of this, you end up getting a number that is the same as the bit mask. 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. Now, what's special about this is that our intention was to check if the fifth and sixth bits were on. Since they are on, the fact that we ended up getting the same operand as in our AND instruction as the result of this operation indicates that, yes, these two bits were truly on. Because the only way that the two bits that we have in the bit mask also appear in the result is if the original registers, those two bits are also 1, which is a very nice and very concise way to check if the bits work the way we want it to work. And finally, we can confirm saying, yes, the check operation is successful, and hashtag 96 confirms that bit 56, bit 5 and bit 6, are indeed on. Then we go to the set operation. Let's say we no longer want to check. We want to actually go and set the fourth and the first bits in the register. What does that mean? We want to change the fourth bit to be 1, and we want the first bit to be a 1 as well. So how exactly do we change existing zeros to be 1s? That's using the O operator, where we again create a bit mask where there is 1 in the positions of where we want to alter. We want to alter the fourth and first bits to be 1s. So we change those bits to have a 1 in the bit mask. Then what do? You perform an O operation and you convert this bit mask into binary, which in this case would yield you the answer of 18. And you do a bitwise O. Perform an O operation on each of these bits. You'll end up getting 0 or 0 is 1, 1, 1. Sorry, I said 1 at the beginning, isn't it? 0 or 0 is 0, 1, 1, 1, 1, 1, 1, 0. So what's special about this? You realize that this bit sequence is exactly the same as the top bit sequence, except bit number 4 and bit number 1, which were previously 0, have now become 1. Perfect. That's exactly what we wanted to do. So if you do an O operation, you can update existing bits to a 1. So there you go. The bit mask being applied on the original register with an O operator ends up giving us the set operation successfully, setting fourth and first bits to the intended output. Then we have the reset operation. Let's say earlier we want to make our zeros 1s. Now we want to make our 1s 0s. Essentially, we want to reset the second bit in our register. We want to make sure that the 1 in the second position is no longer a 1, but instead make it a 0. We want to turn that position off. How do we make that position reset? How do we make that 1 go back to 0? This is a bit interesting. Everybody take a close look at this. Now, if we rely on the previous way that we used to make bit masks, what we'll realize is that we make a bit mask such that the number we are interested in, the second bit, that position, would end up getting a 1. But frankly, this wouldn't work for a reset operation. For a reset operation, we start by creating a bit mask where the bit position where we are interested in to reset, we set that 1. But before we go ahead and make any operations with this, we have to invert this, which is how we end up with the actual bit mask. So we ended up with the original bit mask, you can imagine, of all zeros, but with just a 1 for the second position, because that's what we want to reset. But we invert that, making the entire bit mask the exact opposite of the original yellow color bit mask. So 0 becomes 1, 1 becomes 0. Now you take this inverted bit mask and you perform an AND operation on that. The reset operation, if you recall, is essentially the two operands AND and not combine. No. But frankly, in the exam, you can't combine two assembly code instructions together. So what we do is we perform the not manually. What is the equivalent of performing not manually? That's to invert the bit mask we originally designed manually, which is to make the zeros ones and ones zeros. So that's the not part of this instruction done. Then we can take the binary form. So we can take the binary number corresponding to this inverted number, represented that in denary, and then plug an AND operation in front, which is effectively the same as doing and not the original bit mask, the yellow bit mask, right? And not this yellow bit mask is the same as inverting the yellow bit mask manually and then performing the AND operation. If you do this, you end up getting what? The following result, where all the bits are exactly the way they were originally, except the second bit has been turned off. Do you see that? It's pretty cool, right? You can now reset bits you want by creating a bit mask where there's a 1 in the places you intend to have a 1, but then invert it and then perform an AND operation with the inverted bit mask, which is an equivalent operation to doing and not in succession. Finally, guys, we're at the end. What if you want to toggle? Toggling is making any zeros ones and ones zeros. That's what toggling means. Let's say we want to make the fourth and first bits toggle. That means we want to make the fourth bit 1 a 0, and we want to make the first bit 0 a 1. That's what toggling means. To toggle is very simple. Again, create a bit mask with ones in the interested positions. 4 and 1. Those two positions are what I want to toggle. That becomes your bit mask. And then instead of AND or not, perform an XOR operation where you perform XOR on the binary bit mask, but you can convert it to denary when you write the assembly code instruction as XOR 18. But where did the 18 come from? That's this number's denary representation. You perform XOR on this, and you end up making the fourth bit, which was previously a 1, a 0, and the first bit, which was previously a 0, a 1. All the other bits remain exactly the same. There's a small mistake here, guys. This bit should be a 1 because 1 XOR 0 is a 1. But just to double check, yes, everything else perfectly is correct. But that's it, guys. If you have any questions, do let me know. Do go to the questions given to you on the tute as well. Try to apply what we learned on the tute. But that completes 4.2 Processor Fundamentals. And best of luck for your exams.